Okay, guys, here we go. Bear with me. This is really my first time recording using OBS Studio, etc. Hopefully I can get everything covered. The first thing I want to show is what I'm using for my voltage settings on the Cosmos. Originally I was using 4.5. After some playing with some different settings, I found 2.7 actually probably to be more ideal. Now, as I said, 2.7 isn't actually 2.7. You guys need to check this and verify. You can see here in the notepad. So I've actually measured an input voltage. Now this is with the Auto Ranger, so that way I know Auto Ranger, Cosmos, everything. At 0 dBFS, full scale voltage is 3.3266. Auto Ranger set at -6, -18, -24, and -30 if ever needed. The reason I kind of figured these settings to be the best is because you want it to be as close to 0 dBFS full scale on the ADC, like on the Cosmos, to give you your best resolution. So at 1 watt into 8 ohms, 1.4 dBs, 5 watts into 8 ohms, 0.4 dBs on the 6 dB attenuator, and at 25 volts we got 0.48 dBs on the 18 dB attenuator. And if we flip to -24, we can have a max input into 8 ohms of 347 watts. So that should give us a little cleaner headroom. I haven't tested it yet, but I do have all the voltages and everything set. So that is that. Okay, so just to give you an idea, this is what we're working with right now. That's a rat's nest of USB, so that's just a passive hub. Both the topping USB isolators are connected to the DACs, one to the topping and one to the SMSL. The Cosmos runs straight in without. This is what I found to be the best setup, and that's our cabling right now. So I've got the topping connected to the Auto Ranger on 0, Auto Ranger out to the Cosmos. Okay. So let's go in here. Okay, so REW. Now let's go to sound first. This is one of the most important parts. You can never always change this around. So I like to disable all the devices I'm not using. Properties. Make sure your sampling rate and your bit rate is set, and exclusive is set, both these checked, and this off. Do that for both, or while you're one topping. Then you got this. Like that. And be very careful of this. For some reason, Windows likes to enable this by default. You want to make sure that that's off. So that's all set. Now, every time you open REW, it always defaults to 44. Let's change that to the sampling rate, 192 or 384. I haven't had really any issues with 384. That's what I've been using. Exclusive. These are my buffer settings. I've experimented a little bit with different buffers. Basically, as long as you get a stable output and input, you know that your buffer is okay. This is a fairly fast computer. If you've got a slower computer, you may have to increase those. The only thing else that you need to change on here, maximum amount of measurements, I like to set it at 100. The default is like 30. If you start taking a whole bunch of measurements, then the next thing you know, you fill up and REW starts discarding or won't let you take any new ones, which is a pain in the ass. Levels, so we can see here we got an input level. We got our generator, RTA. A lot of this other stuff is only for room or acoustic measurements. The scope is handy sometimes. EQ you don't need, room sim you don't need. Also too, I use a ultra widescreen monitor. That way it gives me a little bit more real estate that I can have multiple windows open and I don't have to keep minimizing and opening it back up. Settings on here, I like to make sure that the scroll bars are off because I don't like clicking on those by accident. You got log and linear. Log I use majority of the time unless I'm taking say measurements over 10 or 20K. Then I flip it to linear. You can set this to basically whatever you want. I usually use 10 and 185. We got our spectrum, no smoothing. Basically anything you want, 256, 512K. Depending on the frequency, you can even go down to 128. But if you're doing like say 60 hertz or so, you want it higher to get a cleaner picture. So right now we got no signal. So this is our noise floor of the loop back. Negative 126.8 A weighted. We got negative 124.6, 22 to 22K, no weighting. So that's this is a normal. Voltage is 1.9, 1.5 A weighted, which is this is my normal weighting, normal level. Here is where you calibrate. So I've already calibrated. So you can click on here, this little arrow for presets, which is very handy. So I've got 0, 3.32, 66, -6, -18, and -24. So I select that on the auto ranger, then I select that here, and then everything changes. So right now I'm on 0, so I want 0. Also too, this is where you calibrate your output, but I've already calibrated it, so the topping, now you always want to calibrate it loaded because it'll make a big difference. The topping, if I have it unhooked from anything, it puts out well over 2 volts. As soon as it's hooked up to the auto ranger, 1.9162, which is, so if I go 0 dBFS, that'll be 1.9162, or rounds up to 1.2 volts. The nice thing about having this calibrated is you can change 0 dBV. I can do 250 millivolts, whatever I want my signal to be. I don't always have to work in dBFS. Measure both channels of your output device. I found the left channel to be way weaker, so I use the right channel on the topping. So basically we got our sine wave, which is most important. You want to make sure you got dither at 32 bits, or minimum of 24. Anything under that, you can start getting some weird harmonic distortions. Multi-tone is also handy. You can do double tone IMD testing, triple tone, This would give me 31 tones. You know, it's just really handy. Just, well, you can see here. So my sampling rate, how bad this looks. You think, oh no, that doesn't look good, but it's actually the sampling rate that's causing it. See, so if you're only sampling at 128, those all kind of get rounded off. Your high frequencies are okay, not down here. Pink noise. So you can just set this, but you want, if you're doing amplifier, obviously 20 to 20, and then you have a pink noise signal. So I use that um, to warm up the amplifier, burn it in a little bit, heat it up. Um, you can use it pretty much whatever you want. White noise, it's really versatile that way. Okay, so first thing I like to do though, open up our levels. Say set this at -10. We just want to make sure that we're not clipping. Everything looks good. Output is at -10, and we've got lots of headroom on the input. So I like to do a measurement sweep. This we can ignore because we're not concerned with SPL. So we want to take a measurement sweep to see the frequency response and flatness of the topping, the auto ranger, and the input of the ADAC. So 0 to 192 at 0, 2 million, 384 kilohertz. We've got our output right channel, and we hit start. So this just takes a quick sweep. Apply our limit settings. We're in DBR. We want either DBV, DBFS, whatever you guys want to work in for this. Now you can see the roll off, this big phase shift, all of that stuff. This is the raw response. Well, when we measure our amplifier or any device, we don't want this raw response. So we need to create a calibration file. So we go and make sure that this is selected. I'm going to call it D10S raw. I go into here. So sound card calibration. We're going to make cal file. The measurement D10S raw. We hit OK. We can add notes if we want. Save it off somewhere. So I'll save it as this because I took it at 384. If you use a different sampling rate, you should create cal files for each sampling rate. So we'll save that. Yes. Now I don't like to apply the calibration file to all my measurements. I only like to apply it to frequency response. But we can see here, if I do this, sound card, I can load it. And that's our corrected frequency response, which is flat. So that shows us the sound card calibration. I turn that off. There's our phase, 0 degrees. So you'll know that the sound card calibration file is perfect if you have 0 degree. It's basically a phase and it's flat, and this is flat. So when you measure an amplifier, frequency response, change cal, and then you apply that sound card calibration file to it, and then you get the true response of the amplifier. That's pretty much the only thing you need to do there. We go into here. A couple little things that I've noticed. So let's just say 10K for example. Change that. So we want some dBV. Play this. Okay, so there's our distortion. We can change it to percent, decibels. I usually leave that high pass. I'm going to change this so we can have a little bit better look here. So you can see right now, it says our THD is negative 97 dBs. But if you notice here, it's measuring harmonics all the way out as far as this goes. So it's measuring all of these harmonics. So if we want a better idea, we can limit this to 91. And that's actually what our THD is, 115 and a half, not 97. And when we do sweeped measurements, REW only takes into account these. It's only for some reason on the RTA that it calculates to all the harmonics available. So even if we change it to 1K, it's actually measuring it to the 50th harmonic. So we only want 9100. And now we've only got it to the 9th harmonic. And you can see how much of a difference that makes. But this is only really if you're just kind of looking at FFTs, or if you want to grab a picture of this. The only problem is when, say, 1K right now, I'm at 9100. My THD plus N, not a valid reading. I want to grab a picture of this, so I just hit current, and I've got a picture. Obviously, I've got to set my limits. dB relative. And that was that. Basically, we never use peak. That's more for spectrum analysis, sound waves, different things like that. We're only concerned about this guy right here. Another little quirk that I found, I think this is just the way that digital audio works. Let's say roughly 6.2 dBFS, which is 939 millivolts, works out to be about the 25 volt output setting that we normally test at. Change this to 10K. So you can see right now, THD's negative 104. 6.1, 108. 6.0, 109. Then it drops back down. There's little notches. So you got to kind of figure out where the best spot to measure. As you can see, it's either, we're looking at 939 to 960. So 960 millivolts would be our input voltage. That gives us a nice reading at 10K. Then we jump to 20K though. We're at 107. See that? See how fast it drops off? But at 6.1, 110. So I was doing most of my measurements at, I think, negative 6.3 with the topping. Now I've changed most of my measurements. I do at negative 6.1. Just gives it a little bit better resolution at the higher frequencies. And this is pretty apparent. So I've got some measurements I took. So I'll just close these off. example. So here's the D10S. So you can see here, it's nice and smooth. And then we got all these steps. Then it smooths out, and then it starts to climb here. So this was taken at 1 dBFS steps. I changed to here. This was more of a zoomed in. So I took this at 0.1 dBFS. So you can see how much it changes. And I don't think it's anything that's wrong with the devices. I just think that this is the way the digital works. So you want to try and find these little pockets, so that way you can get your cleanest reading, even if it just means by bumping up and down by, you know, 1/10 of a dBFS or so. But another interesting thing, so if I go overlays, distortion, clear selections, there we go. Okay, so you can change this. So right now, this is dBr, so I can go dBr or percent. I don't like scientific notation along here. I wish that this wasn't like this. I don't think it needs to be. dBr. Okay, so right now though, the x-axis is based on my generator voltage. So that's the output voltage of the D10S. So you can see right here, once it hits about 1.2 volts, it starts to really climb. Now this is a power sweep that I took. So you can see here, this is the input voltage then to the Wolverine. So right around basically the same point, we can see that the distortion is climbing before it starts to clip. But it looks like it's climbing at the same rate as what the D10S distortion was climbing at. I just kind of noticed that today. I thought it was pretty neat. But generally, we don't want to use generator for voltage for that axis. We use input. Input voltage, you can see here, we're actually, you know, 36 volts. And we go to watts. So there we are, 165 watts, 190 watts. But it pretty much runs, you know, 124, 125 in that range. What else did I take here? That's those. Frequency response, we went over that. Oh yeah, this is change this to linear. So this is the D10S loop back at 20K. So you can see the harmonics. So the THD came in negative 111. The precision oscillator that I had built, THD negative 127. Basically same voltage. You can see the difference. I wish there was easier ways for REW. You can see how much cleaner the distortion spectrum is. So it'll be interesting to test this out on the Wolverine. I actually have never hooked it up, but I took that today. I think that's pretty much it. Oh, the only thing to remember, so you get all your measurements here, they're gray. Oh, I know, there was one more thing. This is also, so we go back to our RTA window. Okay, this is how we do our automated measurements. Step sign, THD versus level. So we want to test at 1K. We'll just say negative 15 to 0. Two. I'll make it quick, so I'll just do that. 4 averages. Now, silence. We don't necessarily need it, but I found adding 1 or 2 seconds of silence got rid of all my. Sometimes I noticed some bad readings, some funny jumps in the readings, almost like the software couldn't keep up. I found changing this made a big difference. So then you just hit start, and then REW automatically does its thing. It's measuring the noise floor. Let's see here, measuring. Tells you your estimated time remaining. It's just walking through these measurements. Usually when I measure the Wolverine, I do negative 35 to 0. You definitely want to make sure you get this enabled. I usually have it so once it hits 10% THD, it stops the sweep. And there it is. That's that. We go to distortion, and there it is. So you can see now it's blue. That means it's not saved. So we want to hit save all. That'll save all the measurements. Save like that. Yes. Now say for example, if you only wanted to save this measurement to send to somebody, you just click that one, and then I can just save that one and send it off. Step sign also, we've got IMD versus level, THD versus frequency. So we've been normally doing 20 to 48 with one step. Negative 6.1, whatever we said was the best. Now this is the one you got to make sure you select 1 million because we're starting at a low frequency. 2 averages normally is what we've been doing. Start. And software base does the same thing. Now it takes a little bit longer because of the high FFT length. But if you choose a smaller one, then basically anything under 100 hertz isn't very viable. And then blah, 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 just walks through. And that's it. Now the only other thing that I did is I downloaded this macro recorder program. So that way when I want to do repetitive sweeps, I don't have to keep, babysitting the computer. I can just let it do. So this is programmed to do sweeps 20, 500, 1K, 5K, 10K, and 20K. So basically whenever I want to do it, playback, I just hit play, and the macro automatically does its thing, starts all the measurements, and I can just walk away. And in 45 minutes, I come back, and I've got all my measurements. I just found that really handy. It was a bit cumbersome to set up, and I'm sure that there's better ways to do it, but I found it worked pretty good. I've also got another file that I set up for when I do the repetitive sine sweeps. So it's set basically every 5 minutes. And then those are the ones that I usually overlay just to check. think my mic just cut out. Are we back on? Yep. Sorry about that. That's the one I usually use for temperature drift. When I do a whole bunch of measurements and then overlay them just to see. Basically, I think that's about it. If there's anything else, I'm sure I can make another video, but I think that should give you guys a pretty good rundown of kind of what I do and how I have it set up. As I said, REW is a very versatile program. You can do a lot with it. That's why it kind of looks so complicated, but really it's not. Oh, one other, I know what else so I'll close this all off. So so this is an early access build of REW where he's starting to make some changes to the UI and stuff like that. One of the neat features. It was actually one that I kind of recommended because it would be nice to be able to see. Oh, see how slow that was? Because RTA, we got that. -6. We'll change this to 1K. So we can see here, it's got a gain output right in this window, so you can see the gain. So basically, from the topping through the auto ranger, there's a slight reduction in gain, but it's not that high. I kind of like this new UI. It's going to look pretty good, I think, when it gets done. I haven't used it too much. And then Multi-Tone Analyzer is another software program. It's not as good as REW because there's no live measurements. But the one thing I do like about it, so I'll just take a quick reading here. Just gives a lot more detailed data panel. It's more oriented towards DACs and stuff like that than amplifier measurements. But it's nice because it gives you everything: signal noise ratios, THD plus N, your bits, etc., etc. So just another little piece of software. But I think that should pretty much hopefully cover everything. If you guys need anything else covered, just let me know.